Today's lesson is to discuss lenses. And what we have up on top here are two prisms. One's upside down, one's right side up. And you'll see that these light rays parallel to the principal axis tend to refract towards each other. And if you make this prism into more of a lens shape, these light rays parallel to the principal axis will actually meet at the focal point. And so light rays parallel to the principal axis refract through the focal point for a converging lens. The diverging lens, on the other hand, has light rays parallel to the principal axis, will now diverge away from each other. And you'll notice over here that they are diverging away, but if you follow them back through the lens, they do end up meeting at the focal point here. And again, here are two prisms, one upside down, one right side up, just to show the shape of this diverging or concave lens. Our types of lenses are converging lens and diverging lenses. You'll notice that the converging lens all are thicker in the middle and thinner on the edges. And if you look at a diverging lens, they're thinner in the middle and thicker on the edges. Now there's different kinds of converging lenses and diverging lenses, but they all have the same, all converging lenses are thicker in the middle and all diverging lenses are thinner in the middle. When we draw ray diagrams to form an image, we can draw three rays. I typically draw the first and the third ray. The first ray you draw is parallel to the principal axis. It will refract down through the focal point for a converging lens. And the next ray I draw is the light ray that goes through the center of the lens. Now you can also draw the light ray through the focal point and it will come out parallel to the principal axis. For diverging lenses, again, the first light ray you draw is parallel to the principal axis and it will refract upwards, but then when you follow back through, it will go to the focal point. The next light ray I draw is this third one down here, again, just straight through the center of the lens, and we have this light ray going straight through the middle. This middle ray that is drawn here, I don't typically draw. I just draw the first and the last rays. So when we draw these ray diagrams and we have an object out here beyond 2F, and we draw these light rays, they form a real image that's inverted beyond the focal point. It's between F and 2F. If our object starts between F and 2F and we draw our ray diagrams, the real image is out over here. It's larger than the object and it's beyond 2F. 2F should be right here, so it'll end up being beyond 2F. Here's an example of making a real image larger. Whenever you watch the movies, you have your object in between F and 2F. If you place your object in between F and the lens, you end up with a virtual image. Your light rays will diverge on the right-hand side of the lens, and then you have to follow them back through to find your virtual image. A magnifying glass works in this manner. Now the ray diagram for the concave lens is different. It's just one ray diagram. You don't have all these different positions you have to worry about. You have this object here. You draw your light ray parallel to the principal axis. It refracts so it lines up with the focal point. You draw your light ray through the center of the lens, and these are diverging. When you go back through and find their intersection, you'll find this virtual image occurs right here. These types of lenses are used in glasses quite often. The equations we're going to use in this section is 1 over DO plus 1 over DI equals 1 over F. That's the thin lens equation. And the magnification equation is HI over HO equals negative DI over DO. I'm not so much worried about the negative sign in this case, but the negative sign up here for DI or F is important. So here are all the variables we have to know. The focal length F is the distance from the focal point to the lens. The object distance DO is this distance here from the object to the lens. The image distance is from the lens out to the image. The height of the object, HO, is just exactly that, the height of the object, and HI is over here, the height of the image. These are the variables we have to know to be able to solve our equations, solve our problems. The rules we have for this is the focal length is positive for converging lenses and negative for diverging lenses. DO is positive always, and DI is positive for real images and negative for virtual images. So let's do a practice problem here. We have a 1.7 meter tall person is standing 2.5 meters in front of the camera. The camera uses a converging lens whose focal length is 0.05 meters, so then we know it's going to be positive, 0.05. Find the image distance and determine whether the image is real or virtual, and then find the magnification and the height of the image on the film. So what I'd like you to do is pause the video, try this problem out, see if you can solve it, and then I'll have the answers up here in a moment. Write all your givens down and so on. We use the equation 1 over DO plus 1 over DI equals 1 over F, and then you can rearrange the equation to solve for the DI, and you get 0.0510 meters. And since this image distance is a positive number, we know from our rules that it's a real image and it's formed on the film. It's projected onto the film. And then now to find the magnification, we do DI over DO, and that equals 0.0204 is our magnification. And you can also do DI over DO equals HI over HO, or you can just do it as a magnification equation. And that answer, your height of your image with this particular magnification should be 0.0347 meters. I'm not too worried about the negative signs for this part of the problem. Our next problem is an object is placed 7.1 centimeters to the left of a diverging lens whose focal length is negative 5.08 centimeters. And because it's a diverging lens, it has to have a negative focal length. Find the image distance and determine whether the image is real or virtual. Obtain the magnification. So pause the video, please, and go ahead and try this problem. So again, we use our 1 over DO plus 1 over DI equals 1 over F, and we end up with an image distance, a DI value of negative 2.96 centimeters. And with the negative DI value, that means it's a virtual image. And then we use the magnification equation to find out what its magnification is, and we use DI over DO, and it ends up being 0.417 magnification. So actually this image will, since it's less than 1, this image will be smaller than the object.